Time for you.
Okay. Hello everyone who's on the internet. Thank you for coming. Today the room is a bit small. It's almost filled, and we will start the second lecture about entanglement bootstrap. I will continue from the previous lecture. So the setup of the problem. Well, variable that I explained last time, we have a reference state. A reference state on a manifold system. And draw a rectangle, which means we have a disk-like region which is large enough. Large enough means it's larger than the correlation length several times, larger than the correlation length. And each little block, the axis A0 and A1 are satisfied. Yeah. And to be concrete, I will mainly talk about 2+1. This is 2+1 space and dimension, and this large is two-dimensional. So, oh, by the way, lecture 3 will be tomorrow, Saturday from 10 a.m. to 12. And the room is this one. It's slightly larger than this classroom. And it's for graphics day. Yeah.
Happy. Expression. Happy.
Oh, nice. Yeah, so this is for graphics. I think this one is slightly different than the schedule announced maybe a week ago. And so I want to make sure people know that the next lecture is for graphics day. And tutorial 2, yeah, you will give some tutorial discussion about some categorical way to understand graphics system. And build work with by Liang Kong and Hao Zheng. All right. Okay. So one thing we will be able to understand will be this subleading term of entanglement area law, which was famously known as topological entanglement entropy, appeared in the 2 papers in 2005 by 2 groups of authors. And they derived this formula, so some entropy quantity is some subleading term of an entanglement area law of your manifold system is related to the logarithm of the total quantum dimension of atoms. So it's the square root of the sum of individual quantum dimension of atoms. I will try to explain roughly what the quantum dimension means, but the important formula is this one. So a set of integer A, B, C defined by the fusion roots of the atoms. A, B, and C, the integer and B, C will be non-negative integer, which tells you the number of ways A and B can fuse into C. And this equation, well, actually this is not a one equation, but a set of equations, because you can choose different A and B. And choose different A and B from the set of atoms. Then it turns out the dA will be determined. The set of quantum dimension dA will be determined uniquely. By and then BC, the set of integers. This is according to the probability theorem. Yes, some mathematical theorem that can determine the quantum dimension from the integers. But can we understand the subleading term within this framework of entanglement bootstrap? We only have those structureless axioms. We have so there's no much structures. If we really want to derive something like that, we'd better define anion species. How many anions there are in such a system? We need to answer that questions, and we need to define integers and UPC and so on. Yeah, today I'm going to tell you this part of the story to hopefully get to the answer of the subleading term by first define the anions, their antiparticles, their fusion rules, and so on. And on the way, I'll tell you a set of techniques from quantum information that allows us to do such things. Okay, I'll erase this blackboard. All right. So another thing I need to remind you is that something called information convex set. And the exact definition is there. But now let me see this. For any region omega embedded in the background, we can define the information convex set. It's a set of distinct matrices on the region omega satisfy a set of conditions. I won't write the condition here, but it's on that screen. If you are here in person, you can see it. So it's like the set of density matrices are defined on the region omega, but you want to thicken omega by some distance, and then require the local consistency and locally state on the thickened region is the same with the so-called reference state. Did I say this is the reference state? Yeah, this is very important. You need to start with the reference state.
This reference state is global.
Yeah, in some sense it's global. It's on a rectangle. But this is large enough that you see 100 by 100. On the length scale of the coarse-grained lattice. No, it doesn't. The intuition I really have is that you may have a pure state on your entire system. Your entire system could be on a plane. Infinite plane is okay, but typically you have or the system in someone's lab is finite, and the topology may be interesting, maybe not. But the idea is that we take a patch which is large enough, like 1,000 times of the correlation, and then we can use that as the reference state. So in general, if we take a piece out of the entire system, it will be entangled with the rest of the system. So it's a mixed state in general. But axiom A1 actually is called local purity. Local purity. I'll explain this after a few more words about the definition. And axiom A1 is uniformity. Homogeneity or smoothness, if you prefer. Okay, so we have a set of.
Yeah, sorry, I have a question.
Yeah.
Yeah. So in this model, do we need the periodical boundary condition, or open boundary is still okay? Since somehow if we have open boundary conditions, then can we always choose a small patch like this?
Open boundary. You mean this one has an open or periodic?
Oh, this one is more like periodic, right? But if you have some open boundaries, then maybe there is some edge.
Yeah,
So
open
then
boundary
what
is also
happens
fine.
is-
So here, suppose you have a system with an open boundary.
Mhm,
For example, if you have a Tory code, you can have a gapped boundary, but also gapless boundary. And if you have a chiral system, something with non-zero chiral central charge, then all the boundary must be gapless. It is also okay. But now what happens is that I take some region within the bulk. So it's as long as
I
it's
see.
away from the boundary, it should have the entanglement area law, then the axiom should be, we can argue this is a physically motivated.
I see. So we can just choose a patch inside the bulk, but
Yeah.
not. I see. Okay. Thank you.
Thank you. All right. So the information come like that. Yeah, I think I need put the figure from that backup screen to here. So suppose this is omega. Here I choose this to be an annulus, but it could be more general. And the yellow colored one is the thickening, omega plus, omega plus. And we want the state to be consistent on any bounded radius balls contained in omega plus. And yeah, it's like this comes from some state on omega plus, but this state is reduced to the same with sigma on any ball. So it's like you have a set of states that are locally indistinguishable. Locally indistinguishable. And if we are familiar with some solvable models of topological order, like the Tory code and so on, we know that there would be usually we could have multiple locally indistinguishable state on the edge. Actually, yeah. This was explained in the tutorial. Yeah, you do some computation showing that for the Tory code state, if you have the Tory code state and for the annulus, you will have multiple state on the annulus. It's like with the information come like that with the annulus. If we have the Tory code state, the answer would be you have a set of it's a convex set, so you have a convex combination of some state. You have sum of A, probability P of A, and so the set of extreme points. This is extreme point. Where the set of labels will be ran over all the ion types 1E and N. And those extreme points satisfy some conditions, like they are orthogonal. So when A is not equal to B, they are orthogonal. As density matrices, well, let me specify the region. So the region is on this angle. And as density matrices, we can compute the entropy as well. So the S of A and equal to S of 1, where 1 is the reference state reduced to the ball. Yeah. Why should this be reasonable? Well, we are not just going to. What?
What's the definition of orthogonal here? How can we define orthogonality?
Speaker, sorry, I couldn't quite hear you. Could you speak again? I'm changing the.
Okay. Yeah. I want to ask how can we define the orthogonality here?
Okay. Good. So for two pure state, we can use the inner product, but now we have two mixed state. So your question is a good one. For quantum information, in quantum information, there are multiple ways to define orthogonality. A convenient way is to talk about fidelity. Fidelity between two states, alpha and beta, to mixed state alpha and beta, is defined to be piece of square root alpha to the beta alpha and a half. Some people have square here, but anyway, so it's something you can compute from two density matrices. The two density matrices need to be supported on the same region. So you can compute this. If fidelity give you 0, then we say the two states are orthogonal.
I see. Thank you.
Okay, great.
And I have a related question. So in this case, can we just construct the project to the each anion sector and see the projector is orthogonal to each other?
Right, for the Taylor code, we can
It's
do that.
equivalent. I see.
Yeah, so in many solvable model, we can use this approach. Right.
I see.
Yeah.
I see. Thank you.
And we will going to give a proof that's based on the axioms. Then we don't assume the solvable models. Could hopefully be more general. And the thing is that
Sorry, is that the fact that they're orthogonal can be proved using A0 and A1, these two axioms?
yeah, I'm going to talk about that. Yeah. Okay, I'm going to talk about exactly one more thing of the target code example before going to the general case, and before explaining the local purity, why 0 is local purity. But let me say the following. So the intuitive picture we should have is that each extreme point correspond to some excited state of the target code. Is A created within the whole of the annulus, and A bar somewhere outside the annulus. And there is a string operator passes through the annulus, but the string operator is deformable, and therefore the local density matrix does not detect the string. Only the global density could see different, and they are very different. They are orthogonal. The states are orthogonal on the annulus. And I want to talk about something that Michael Lehman and Xiaogang Wen thought about when they wrote the topological entanglement entropy paper. When they partitioned the annulus into pieces, into A and B. So the B is the union of the left and the right. And if we take any of the extreme point, we find we can compute the condition of mutual information.
Sorry, I have a question.
Oh, sure.
Suppose we deform the annulus a little bit.
Yeah.
Does that change the information convex set?
It's not. It will be a zero. Yeah.
Okay.
That's
and then
important.
I have a question. Suppose we put the entire G plus 1D's model on a sphere. Okay. And I have a string line connecting A on the north pole and A bar on the south pole.
Good.
And then basically I should expect that let me think. The information convex set built from that's surrounding A and A bar basically the same. And okay then.
Yeah, they are isomorphic.
Okay.
Yeah, the sets are isomorphic. You have some map from extreme point to extreme point. The structures are the same.
Okay, but then how do I understand the orthogonality of the extreme?
Okay. If we talk about third code, then we can think about projectors. That's one way. the projector, I think you do consider this is a one plus some X string operator.
Yeah, for a Tor code case, that's obvious, but for generic case, when like A does not equal to A.
A is not equal to A, but right, generically it's not. Yeah. But still there's some projective measurement that can distinguish A and B, right? Yeah, I will give better explanation later using the axiom. We can actually prove the orthogonality. But for now, let me make a remark. It's like you take any state, any extreme point, you compute the condition mutual information, which let's recall the definition of SAB plus SBC minus SB minus SBC. And for the Tori code, you have log because you have 4 different extreme points. Well, but let's try to, well, because we have a convex set, in fact, I think I better draw a picture. So we can see, this is like this simplex. This is the simplex. There's 4 extreme points. Rho 1, rho E, rho F, and rho F. And a basic property of entanglement entropy, S of something is entanglement entropy, or the von Neumann entropy is defined like a trace minus trace rho log rho. And that quantity has the property that if you do a convex combination of 2 quantum states, the entropy can only go up. So you can tell that if you find something with a larger entropy, you want to pick something in the middle. Let's put a star here and consider some rho star. So which state has the maximum entropy? The maximum entropy state, rho star, will be the convex combination of all the 4 extreme points. And then let's ask what's the conditional mutual information for rho star. Again, we need to write the 4 terms, SAB, SBC, SP, and SABC. But the states are actually indistinguishable on AB, BC, and B because AB is a disk, BC is this one, BC is another disk, B is the union of 2 disks. Their information convex sets are not interesting, they always reduce to the reference state. So the only difference between rho A and rho star would be this term. So this term makes a difference. So yeah, so we can easily compute the entropy difference. So it turns out this one gives you 0. So we find a quantum Markov state. And I assume we still remember that the quantum Markov state is defined in the state with vanishing conditional mutual information. But let me write it here. Quantum Markov state. Your ABC is defined to be with defining property. All right. So somehow we are able to find quantum Markov state in the convex set. That's the state with the maximum entropy. Yeah, this is true on this model, but we can ask whether this is true in general. It turns out it's a general thing. So as long as we have the reference state, we can define the information convex set and the maximum entropy state in the convex set of the annulus. is the Markov state. So what's the intuition here? The intuition, well, this is quite non-trivial. I will try to sketch the proof why this is true. But intuitively, this makes sense because what's the maximal entropy state? It's entropy is high. Whenever entropy is high, that means then we don't have much knowledge. If we don't have much knowledge, it could be determined by pieces. There will be more hope to determine the state by the pieces. That's not a proof, but it does seem to suggest that the maximal entropy state should be easier to reconstruct from local pieces, where the extreme points are harder to understand, and the very existence of them is quite non-trivial. And if we can understand the entire convex set, that sounds like some non-trivial pieces of work. Then that will be what we will be able to do. Okay. Any questions before I erase the blackboard?
From computing that neutral information.
Yeah.
I just like the first one.
Yeah.
I'm using the formula of logical entanglement entropy or just
Oh, okay, good. So I'm using this one. So let me write the formula here. So it's like so the normal entropy of a sum, CA of UA, will be sum of A. I suppose those states are orthogonal, mutually orthogonal. Then we have sum of probability and minus CA plus A. EA as UA. Yeah, only when the states are orthogonal you have this formula. And then you can try to maximize the probability, and you find the equal probability for this case will give you the maximal entropy.
okay.
Yeah. Now I'm going to explain some basic property of the information convex set. But before that, I want to say some even simpler things related to the interpretation of the axioms. The axiom A0, it might be a little bit mysterious, but let me first tell you that starting from a disk, so this is a disk, it's not so different from starting from a sphere. So we can get the sphere with the following trick. So first we purify this disk with the purifying region for R. We carry some Hilbert space. We create an entangled pure state between this thing and the system. And then we do some logical trick of collecting the boundary. So we have this. The yellow part is the second boundary of the disk. So let's try to collapse the second boundary to a single point. And we insert the purifying region to the same point. Then we get a state on the sphere with a purification point or a completion point. So in this hydraulic diamond, and in this diamond it contains the second boundary. It's like thickening boundary, and the purifying region, the box, the purification box. We put it in the middle, and we group all such Hilbert space into a single cell. Yeah, you may think there's a lot of stuff, right? You have a lot of size in the yellow region, but it's a finite dimensional Hilbert space, and this purification box is another finite dimensional Hilbert space. If we put them all together, it's still finite dimensional. And we get a state on the sphere. So some different state on the sphere. First state.
You mean it's essentially equivalent to gluing them together?
Yeah.
Entanglement is to glue this and some other this like thing.
Yeah. We glue the thickening boundary and the purification region together. And there is a non-trivial check. So it's easy to check that for those small disks, axiom A0 and A1 are satisfied. But we have to check that if we have an axiom or a disk centered at the completion point, we need to ask whether axiom A0 and A1 are still satisfied. Are A0 and A1 centered at the completion point. Okay, it turns out the answer is yes. The reason is that it follows from a very simple fact. So for any pure state, B, C, and D, delta B, C, and D equal to delta B, A, and B. So let's suppose this containing the completion point is A, and now we partition this annual line into B and B, and the rest is C. So we know that on BCD, because BC and D, or BC and D is topologically the same with this. So say it's here, and B and D there, and you can even draw this in the original figure. So that this having and C, B and D there. Right. So after grouping, this B, C, and D will be just those qubits. You deform it in a topological way and put it on the sphere. And so this one is still true. Following from the thing Yizhou explained in the tutorial, is like the axiom on finite length scale implies the axiom put on larger length scale. So this is an example of the axiom on larger length scale. So that's true. Then you flip A and C. Yeah. So the axiom centered at the completion point is true as well.
Oh, that's it. If I successfully purify it, then that delta BCD is equal to delta BAD. But then delta BCD, you already showed that is 0.
Yeah.
So it must be true for delta BAD as long as I manage to purify it.
Yeah, that's right. And right, so it start from this, you can construct a state on the sphere, satisfy all the axioms. And if you already have a sphere, you can remove a point, then you get a disk. So they are the two different starting points are not so different. Okay. The causality or actually with another lemma to understand axiom. Well, yeah, that's for axiom A1, yes. Yeah, we check that axiom A1 is okay, the same for A0. We just make D to be the empty set is okay.
So in your purification process, can you always find such purification that somehow preserves the locality?
No, it does not have to preserve locality. The locality is related to where you put the purification box. And here we decided to put the box in some site. We group the site, call it a cell in the coarse grain lattice. Then the locality becomes good. Alright.
Yeah, but so do you expect the purified state to be the unique ground state from local ammonia? Suppose it's satisfied zero.
That's a good question. Actually, the answer is yes. The answer is yes if we have exact satisfy the axiom. So yeah, those two entropy conditions A0 and A1 are entropy conditions. Something equals to 0. If the 0 equal to 0 is exactly equal to 0, then we can find a commuting projector parallel Hamiltonian for the state.
Just like a torque code.
Kind of, but the commuting projector Hamiltonian can capture more phase of matter, but actually for chiral stay with a non-zero chiral central charge, still gap state, but chiral, then we don't expect A0 and A1 to be held exactly if you have a local, like a finite dimensional local Hilbert space. But then the axiom will be true approximately. Some of our proof can be extended to that context. But the parent Hamiltonian conclusion I used to answer your question, that one is not a robust result. So we don't have proof of this parent Hamiltonian with the approximate error law. Okay, I guess I sort of explained the purity part, A0, but now for A1, the A1 is the uniformity. What do I mean? It's related to the following theorem. So there's a very, very important theorem. About information convex set. It says that two information convex sets are isomorphic. Omega can be smoothly deformed to omega prime. So this one is called isomorphism. And this is saying the two regions can be deformed to each other on the background. Deformable on the background. Okay, and let's give some name of the background. Let's call it A. And yeah,
That's a movement of steps or as linear spaces or so.
yeah, that's something I need to explain. Let me find some space. I'll say it around here. The first is isomorphism as convex set. I suppose, yeah, that's phi be the map from sigma omega, the information convex set on region omega, to the information convex set on the region omega prime. Then, first of all, this is a isomorphism of the convex set. It's like saying phi on P of U. Then 1 minus P of times lambda equals to E.
I know.
Thank you.
So what is Entanglement condition?
Sorry.
Only the deformable in the background and for example.
N, for example, N could be a disk or the sphere, for example. And let me give you some examples. Yeah. So let me draw some figures. So deformable on a disk. And let me give you an example that omega, it becomes omega prime on the background of the disk. So for instance, we can analyze. Here, we want to deform this to another analyze. Like this. Yeah, deform the angles from the left to the right. But what do we do? What do we mean by deformation? We define the deformation as a sequence of elementary steps. Sequence. And one elementary step is like this. So you have a region omega with some boundary. This is the entanglement boundary. So something cut in the bulk. But then let's take some local disk, and suppose this is the configuration allowed by axiom A0. Sorry, A1. Remember that A1 refers to some partition of the disk. And suppose this is the one allowed configuration of this partition of B, C, and D. And then we are allowed to add a bump. So like some topologically trivial deformation of the entanglement boundary. So from here to here. Yeah. Like remove this, yeah. Deform this one to that one. If we have a sequence, a finite sequence of elementary steps, then we are okay. So you can imagine that you deform this annulus on the left to the annulus on the right by a finite sequence of elementary steps. Elementary steps on your coarse grain lattice. Yeah, then it's okay. And right, and you can do this on the sphere as well. So on the sphere, you may have this annulus. You want to deform it here. And here is an exercise. Imagine two different topologically inequivalent ways to do that. Having an annulus is called x0 and x1. X0 deform this to x1 on the sphere. Yeah, so can you think of inequivalent ways of doing that? Okay, let me put the exercise here, and now I'm going to complete the definition of isomorphism. So yeah, I haven't finished answering your question. The first is the map from sigma omega to sigma omega prime must be an isomorphism of the convex set. So take two elements. Then you can pull out the probabilities. And this is a Distance matrix. This is another Distance matrix. Yeah.
We mean in the process of moving, we cross any also.
Right. Well, first we have the reference state. The reference state will be understood as a state with no anyons at all.
Oh.
Yeah, and then you use use some quantum channel. Yeah, actually, I'll tell you the map. Maybe I'll do it again. So phi. So if I call the region as a C, B, and A, Yeah, it's like omega equal to VB and omega prime equal to ABC. Yeah, this is for an elementary step. So for an elementary step, we add or delete a region. So this is an elementary step of extension where we add a little disk C near the entanglement boundary in a topologically trivial way. And this map, it turns out will be a quantum channel, and it will be equal to the quantum channel from B to C based on the reference state acting on UAB. This is called the path recovery map. Or maybe I should write this. So what do I mean? Sigma with E as sigma from B to BC acting on something equal to, first we do the reference state on B to the minus a half power minus a half power on B. Then with the reference state on BC to the plus a half power. Yeah. Yeah, so this is the map from something to this one. It turns out this is a completely positive trace preserving map, CPTP map, known in the quantum information community. Or the more common word will be quantum channel. So it's not a measurement, but yeah, something follows some set of simple rules. It's like the convex set of states on this angular suppose, and then you want to deform the state, letting this region to the boundary. And you can the key point is that you can use the same map for any states in the convex set. Yeah, so you don't need to know the knowledge, like which extreme point you have. You use the vacuum, the knowledge of the reference state. Then you can deform the entire convex set.
Hi, Bowen, can I ask a question?
Yeah.
So when you do the deformation, do you need to keep the boundary smooth? Because I think you want to avoid the contribution from the corners to the entanglement entropy.
Not really. Yeah. Thank you for bring up the corner contribution thing. I actually wanted to comment on this at some point, but the answer is simple. We don't need to worry about the corner for a simple reason. When should we worry about the corner? So only when we have like a that's the distinction. The distinction is that suppose we partition the region near the point into 4 pieces, A, B, C, and D. Then we need to worry about the corner contribution. But in the entanglement bootstrap, at least the part of a story I have been telling, the coarse-grained lattice will have at most 3 regions near a point. In that context, all the corner contribution will be cancelled automatically.
Oh, I see. So when you add the bump, it can be arbitrary, like sharp.
Yeah, in some sense that's right. So it can be sharp as long as we are working on the coarse-grained lattice, and we have checked the axiom on this length scale.
Thank you.
Yeah. The paper, the reference for corner contribution, which was interesting when to check this one. Some of my collaborators. All right. Okay, I still need to finish the definition of isomorphism. So it's isomorphism as a convex set, but that's the simplest condition. We need something finer than that, something better. What's the next? So the next thing is turns out to be the distance measure. Let D be any distance measure between rho and lambda. It will be preserved. For instance, this could be the relative entropy, fidelity, trace distance, and so on. And certainly the entropy difference are preserved. Yeah, I think that's all. All right. So I would say that the theorem, which I like to call it isomorphism theorem.
How do I understand the last condition?
How do I understand
Yeah,
this
the
one?
theorem, yeah.
Okay. Yeah. This is related to the Markov state condition. Yeah, that's a good question. So let me sketch it. So you have C and A plus omega B and omega I is ABC. B and C are contained in the disk, so I can add the region D. So BCD is a disk that you impose the axiom. So it turns out rho and lambda would be here would be rho AB and lambda AB. Here's this is some state. Let me call it rho ABC. And lambda ABC. From this axiom, so axiom A1 on BC and D implies that this state rho and lambda on ABC will be a quantum Markov state. So the right hand side, is this part. Will be ABC. But because of the Markov state property, we can split this thing into 3 terms. As UAB, UAC minus 0B minus the same thing with the rho replaced to lambda AB. Lambda BC. And B and C are contained in the ball. And within this small ball, the states are both rho and lambda agree with the reference state. So the state rho BC are really sigma BC. And rho B is sigma B with the reference state on B. And similarly, lambda on B and BC would be sigma. And they cancel out. Yeah, so you're left with S rho G minus S lambda AP, so that's the left hand side.
So it's kind of a requirement that like the image of phi is satisfied A1 or
Yeah, you see everything is related to A1. So from the very definition of an elementary step that uses the configuration of A1. And yeah, from there to the proof also explicitly use A1. So that's part of the reason that A1 is called uniformity. You can transport the region to another in a topological way. All right. So after this, I will sketch some consequences. So this is really a big theorem, but now we don't know much structure yet. I didn't tell you why there should be anions. There should be now we have the statement that the information should be topological. It can be smoothly deformed on the background. But soon, very soon, we will have some stronger statements. That's a multi-term theorem. Okay, let me talk about the annulus. Yeah, I'll call it X. So for annulus, the information of that set is a syntax. Yeah, that's a theorem. With the fidelity between two points equal to 0. Yeah, I defined fidelity in one of the previous blackboard and then I erased it. But the intuition that fidelity measures the overlap between two mixed states. So fidelity is something between 0 and 1. You contrast in beta is less than the fidelity of the reduced density matrix. And fidelity divided into states. So between 0 and 1. Yeah, it turns out we can show that for two extreme points, maybe two different extreme points. Yeah, this is a very fundamental theorem. So it says you must have a simplex with some extreme point, and this extreme point are orthogonal. And following from there, you can actually show that there will be a finite set. U1 will be the reference state. How do you prove that? So maybe first let me give you some intuition. So consider a spin chain with a spin point upward. Let me call this as state alpha. The tensor of the tensor product state with the state on each side with spin pointing up. But now let's rotate this spin a little bit. State beta and to be a tensor product of the rotated spin. Now let's consider the overlap between alpha and beta. Of course, they are not the same state, but in the overlap between the up to the counted spin to the nth power if we have n spins. And even if we just rotate the spin a little bit, such that this number is very close to 1, slightly smaller than 1. Even in that case, when we increase the number of spins, the overlap will become smaller and smaller, and will go to 0 and larger limit. Okay, 0 or 10 minutes now. And here the proof is in some senses in the same spirit, because now we have an annulus, but we can deform the annulus in some way, make it larger and so on. So in some sense we have a lot of layers. So think of the annulus as some onion. An onion with many layers. Then this figure is kind of similar with this one. But the actual proof, if I write the proof in our paper, you won't be able to see this picture. Let me tell you the sketch of the proof. The alpha and beta belong to the set of extreme points of the information convex set of the annulus. By the isomorphism theorem, it says alpha, the fidelity between alpha and beta is the same with that's for any x tilde and the beta x tilde if we can deform x to x tilde. For example, x tilde is L and R in the following way. So here we have the annulus we partition into 3 pieces: left, middle, and right. Yeah, so 3 concentric annulus. From this condition, so if we look at subsystem, the fidelity will be larger. So this will be smaller concrete. To trace out the middle, and we reach the middle, we have 2 separate concentric annulus separated by some distance, L and R. And the third one I didn't explain, but this is a property of the extreme point. Is that alpha reduced to L union with R is simply alpha and L tensor with alpha R. And given this property, we can simplify the fidelity for the alpha and beta reduced to L and R into a product. F and so it's denoting the fidelity on the subsystem L and R. So,
Not get what the intention of algebra at all.
yeah, this I haven't explained, but let me get some space somewhere to see what is the case. But at least I want to tell you the more general result. So lemma or the factorization property. Factorization of extreme function. It says that for any omega, we take an extreme point of sigma omega. Then the entropy is up to omega. So here omega is the entire region, and omega minus the second boundary. So part of omega is the second boundary. So the entropy of those two equal to the entropy of the state on the second boundary.
Only on the boundary.
Yeah. But one can that imply this one that takes some step. So it's like let me draw a better endless. So this is the endless. We call it X. And now we can partition this into many layers. Okay. So this one. Right, it's something. Okay. So this is supposed to be only like a partition of the annulus. Yeah, so imagine go around. Yeah. From the factorization property, it says that delta dv C and M set is 0, which implies the neutral information between C and R is 0. Yeah, suppose you take your extreme point reduced to B, C, and D, the sub-annulus is also an extreme point. Therefore, you can use the factorization property, which says you put C in the middle and BC is the buffer. Then delta is 0, and that implies that the interior of this part. The C is the interior of this part. It cannot be correlated with anything outside B, C, and D. So the mutual information between C and R will be 0 for this extreme point. But now you can, well, this is not quite L and R, but by the isomorphism theorem, you can enlarge C by some include something, deform it to L. So the correlation between L and R will be vanishing.
Oh, because there's a buffer.
Yeah.
And so L and R are essential references, as long as they're separated by something.
Yeah.
That is like a gap. Intuitively, what do you think a gap phase should be like? A little bit separated, larger than correlation length, then they're almost like vectors, is it something?
Right. The intuition is correct, although we really need to confirm it, because if you take a non-extreme point, there will be some correlation.
That's right. I see.
Right. Okay. So given this 1, 2, 3, the 3 point, what we have is that the fidelity is less or equal to the fidelity square. Or is it hard to see? So fidelity is less or equal to fidelity square. But nonetheless, fidelity is some value between 0 to 1. There's not many solutions. The only solutions we have are f equal to 0 and f equal to 1. So we can either 0 or 1. Yeah, when the fidelity is 0, that means the two states are orthogonal as claimed when the same is 0. And fidelity is 0. Yeah, orthogonal state. The other option is that fidelity is 1. What it means is the two states are identical, exactly the same. Yeah. So yeah, that's the main proof sketch. Any questions with this? All right. So hope this is clear. Yeah, can you tell the two are actually the same thing? Probably looks very different, right? All right, so actually I didn't explain this one. Yeah, this one also needs some explanation. It turns out that this factorization property, first is holds for the extreme point. Second, if this is true, then the state is the extreme point. So in order to show that the reference state is one of the extreme points, we just need to check this property. And this is true. It follows from axiom A0, essentially. Yeah. So that completes the proof sketch. All right, I think I need to go faster from here, but I still need to tell you how to define antiparticles and how to constrain the fusion rules and so on. But let me set a topic. This is something that's very intriguing, and with the problem that originally got me into this business of trying to derive something from constraint. So given that we have the simplex, actually it's before the theorem was proved, so it's more like some conjecture I wanted to play with. Because we have an angles called x, so we have different set of extreme points correspond to angles. Set of angles. Well, I guess in entanglement bootstrap, we first prove the simplex theorem. Then we know that there will be a finite set of extreme points. Then we like to define angles by the extreme point. So after that definition, I will be justified to call them as angles. But to be honest, I should tell you about the breeding statistic to call it angles. But that will be in the next lecture. I believe it's on Monday, next Monday. I'll tell you about gradient statistics. But for now, suppose we have this set of extreme points, and let's define the entropy difference divided by 2. A minus 1. Yeah, so we can define f of A to be the entropy difference divided by 2. And f of A is invariant due to the isomorphism theorem. So we can deform the annulus. The entropy of each state will change, but the entropy difference between two extreme points is conserved. So it's a conserved computing. It's something topological. Here topological means invariant under the deformation, so it's something meaningful. And therefore we want to know what it is. It turns out, we will be able to constrain the quantity. First of all, it turns out f of A is greater or equal to 0. More strongly, we define C of A equal to the exponential f of A, it will be greater or equal to 1. But it's more strongly constrained in some sense. I want to talk about that. Talk about how to understand this this entropy difference.
So sorry, what is it for exponent? The default one,
This is 1. Yeah, this is a vacuum.
I have another question. So is there any specific reason we choose the denominator as a 2 or it's just a convention?
This is a convention.
I see. Okay, thank you.
So at this point, the vacuum is understood to be not degenerative. So that I can say certain thing is 1.
Right, so the vacuum is defined as follows. The vacuum state. 0 of 1 on the integers is defined to be the reference state reduced to the endless. Yeah. Okay. Before proceed, let me there's a few very simple conclusions without proof, because I think it's worth knowing, even if I don't get time to do that. I think I said this last time. For this, the information convex set is trivial in the sense that you only have the vacuum state in it. And for the sphere, for instance, the sphere obtained by the completion, you have a single state, it's a pure state on the sphere. And obviously some other choices of embedded region, a region that can be embedded in either the disk or the sphere will be an N-hole disk. Is related to some fusion properties. Okay, if 1 2 is really N to B. Imagine you have some. The second boundary. The second boundary of the region is a union of a few annuli. So the inner annuli are labeled, can be labeled by some string points, A1, A2, and so on. And the one on the outer boundary will be, has some label. It's determined by the fusion rule. Fusion. And the most fundamental one will be the two-hole disk. This one has subsets. C of this. What's the definition of the subset? The subset is a convex set. And you have state. Or let's call the two-hole disk as a Y. The dual Y belongs to the information convex set, but with some additional requirement. It will reduce to the 3 annuli. The 3 annuli in the boundary. Call them x1, x2, and the one outside is x3. Reduced to x1 is some extreme point. So if you x1 with a. Okay. So the following are claims. It's not easy to understand, but it's something we are able to prove. The sequence of Y is a convex combination of with all A, B, and C of sequence ABC. So you take all the subset, you do a convex combination, but by the convex or C, O, and B says the convex combination or the convex whole of those convex set. That's the smallest convex set that contains all the points in each of the convex set. So that's information convex set. And the second statement is about the subset. Yeah, so the first statement is why the subsets are important. The second one is on the structure of them. Y is isomorphic to the state space of some finite dimensional Hilbert space. The meaning of isomorphism is the same as Euler. It says isomorphism as a convex set in the geometrical sense, but it also preserves the distance measures and the entropy difference. Okay. And then the numbers, the dimension of this finite dimensional Hilbert space will give you some integers. The integers of A, B, and C. These are, we call it fusion multiplicities. Well, I guess I want to sketch what this means. So here's the value of A, B, C. This is the set the set S of the space. And the set S is called the state space. It's the space of all decimal matrices. So suppose the A, B, C is 0, and the state space will be empty set. So you don't have any state. And when you have the A, B, C equal to 1, that means you have a one-dimensional Hilbert space, and you find the entire set of decimal matrices on it. That will be just a unique choice. You have a point. And if A, B, C is 2, you have a decimal matrices on the qubit on two-dimensional Hilbert space. That's famously known as a block sphere. So you have a sphere, two-dimensional sphere with the interior. So it's a solid ball. Yeah, so that's a picture we should have in mind. And in particular, it's possible to have some integer greater than 1. When that happens, we will see some quantum information included in the two-hole disk. So that's very different from the simplex theorem. So this simplex theorem tells you that you have a simplex with a couple of extreme points, and the information will be classical information. But now for the n-hole disk, because we have some fusion space, sometimes the information is quantum. can be quantum.
I think there's a brief remark while we consider unenclosed disks, because topologically this is equivalent to the pens with MNEX, and for example, the surgery and topological quantum field theory. Never really like.
Good, yeah, that's a good point. So now let me, talk about this. I think it usually means the following: in topological quantum field theory, in the sense of by some mathematicians, they talk about axioms on the elements. Yeah, which this is the truth. So we can give you the so-called super selection sectors. And there is a separate axiom on this one, like a pair of pens. If we and some careful space with some integer a, b, c. With that, you can glue all of them to get different topological manifolds. The instance you can create something with multiples, like gluing. Here is a gluing of a pair of pens and so on. Yeah, that's what you need. Yeah. Good. So in that framework, you have axioms about the annualized axioms about two-hole disks. But now in entanglement bootstrap, we don't have them. We derive them. Derive them from local constraint. It turns out, yeah, the derivable local constraint plus some quantum information allows you to recover those rules without assuming them.
So when you say quantum information, what do you mean?
I mean, like the proof of simplex theorem using the fidelity and some detail I didn't show you. They all about quantum mapping.
I think she wants to ask what's the condition between the syntax and the Hilbert space, fusion Hilbert space.
Yes.
The syntax contains classical information,
Yeah,
and the fusion Hilbert space contains quantum information.
Yeah.
So what is quantum information and what is classical information?
By quantum information, I simply mean some information that cannot be copied. It's like if you have a toric code on the torus, you can store the two qubits of a topological quantum information, because you can create a state correspond to some coherent state, some coherent superposition of the foreground state. But you cannot copy them. There's no cloning theorem.
Right. So, but then what happened on the quantum information simplex? Do you mean that my state is actually, my global state is actually unique?
Global, the reference state.
I still don't get. Sorry, but it's the first question. What is quantum and classical?
Okay. So I think that a simple answer would be so by classical, I mean something that you can copy. But this annulus, right? You can make the annulus thicker and thicker, and then you can get a sub-annulus from it. You carry the same information as the original one, so you can share these two different multiple persons. Each of them get the same information. But for two-hole disk, even topologically we can have some insight about this. The question to ask is whether we can split the two-hole disk into two identical copies. Like, it's hard to do that, right? We can certainly split this in half, but the left half will be an annulus, and the right half is another annulus. You don't see if you give them to two different persons, neither of them can see the quantum part of the information.
And I think another perspective is that in the information content and annulus, we do not have coherent superposition, only canonical. If you have a two of this, you have in some sense fusion spaces, you can store coherent superposition.
all of the reason I can get the blocks that it looks like entanglement. But in the original information syntax, the only the entire set of syntax has no entanglement. Then I think same to different types of that, the no entangled.
I'm not sure whether it's proper to say entangled. I prefer to say linear superposition.
But this, if I have a density matrix that looks like in A row A,
Yeah.
then there's no entanglement. This is just classical. This is just classical.
Yeah.
That
Yeah, it's a classical. It's a classical combination of the
this,
orthogonal state.
this kind of density matrix has no entanglement.
Yeah, it's like a right. It's like a p times 0, 0. Plus 1 minus p times 1, 1, 1. Yeah, this state is the classical.
Right.
Yeah.
Okay, again, you're saying that is the density in the information simplex. Some of the density matrices would be intrinsically quantum.
Right. Yeah, this one could be quantum.
Yeah, I see.
Yeah, this is quantum. Yeah, I should make the analog much earlier. Thank you. Yeah. Okay. Now I will talk about two very important ideas. I will try to do this in 10 minutes. So, or maybe I say that the most important idea is to look at the information in different ways. So it's like we talk about total disk and annulus, right? And there is a piece of puzzle we want to solve. We want to understand the entropy difference between different extreme points. It turns out that was very surprising to me that the entropy difference can be figured out by looking at how the information is distributed from some regions. It's like suppose we have a two-hole disk, and we topologically deform it to make it more visible. So you can have the left and the right. So it's a two-hole disk, right? See that? The same with the two-hole disk. But not in this way. For this one, suppose we have some state. Take some state. Take some state in the information common set of the two-hole disk. And suppose so reduce to the left. Zero reduced to x1 is 0 of A. That's one. Yeah. And one question we can ask is that how many states are there? And how do we identify the state in a block sphere, and not block sphere, but rather it is a convex sum of A, B, and C. I only need to sum of A and B. Oh, sorry, sum of C. Yeah, so it's some state. This is contained in this one, but we know that the state rho will be in this convex set. So the question would be, how can we understand the state from the perspective of a two-hole disk and the information of the pieces? Here is the important.
Sorry. Here's the point. When you drop row and then point to sigma CAB on left corner. Down, what you just do.
Down.
Here. What do you mean, row pointing to sigma CAB? What is that?
And I'm thinking I take a state from this set.
Inside this context or?
Yeah, inside this thing.
Oh, sorry. Inside one of this or the whole convex or with ABC or two fixed?
Let's fix A and B.
So fix A and B but not C.
Yeah. Right. So let's compare two viewpoints. I'm going to derive a very important equation. And I believe this proof contains some important idea in it. So it's like, let's compare two viewpoints. The one is that we only know the individual annualize, the left one x1, and the other one is x2. And the other viewpoint is suppose we know the total disk. In other words, we know the knowledge of UIUC. We want to understand the entropy difference of some state. So I want to consider the most uncertain state, so the state with the least knowledge. So in the convex set, you have a convex set of quantum state. Usually it's quantum. You will have some fusion, non-trivial fusion space. But let's try to fix A and B. So put A in this pole and try B in the other pole. And let's ask which state has the least knowledge. And as I argued some time ago by considering the annulus, I do a mixture of topological chart. The state with the least knowledge should be the maximal entropy state. You want to have maximal entropy state from the set, from this set. I think I want to give it a name, so let's call it inside a field of total disk. So I want to consider the maximal entropy state in this set. And we can view the state from the local pieces. So the idea is that if we take the maximal entropy state, because it has least knowledge, we can extend that from the local pieces. And we compare A and B with the vacuum. So if we look at the two annuli, we can see some difference between this state with the vacuum. The entropy is different by 2FA plus 2F of B. Yeah, so this is the entropy difference. On this side, we see a total disk, so we have 3 entanglement boundary, and we have A and B fixed. So the entropy difference will be, you have a different expression about it. You should have an F of A plus F of B. And suppose the outer boundary at the charge C, then we should have a F of C. But in general, the fusion of A and B give you multiple choices of C, the sum of C and BC of C. So there could be multiple choices of charges on the outer boundary, and each has some integer associated with it. But which one is the one with the maximal entropy? The maximal entropy state max on the two-hole disk is it's related to this number. The sum of different C first of all. You something. Yeah, we can figure this out. But the idea is that this requires knowledge of NABC. And this won't be determined by some fixed number, fixed species of C. Rather, it should be replaced by something. So in fact, this should be I think it's an algorithm. ABC into the of C. Yeah. Yeah, so this formula, if you have a unique choice of C, and then if n is a 1, then you get the formula I wrote, but this is a more general one. All right. So we get two different ways to compute the same quantity. The entropy difference. Suppose they are the same. Give the same result. Yeah, what we have is algorithm. So say ABC into 1. Yes. So in other words, we need to get some space. In other words, we have exponential entropy. Exponential entropy. Sum of C. Yeah. So by matching the left-hand side and the right-hand side, in other words, by matching two different views of computing the entropy difference, the entropy difference between the choices with A and B and the vacuum. Yeah, we find this equation. So actually, this equation will determine FA from ABC. So there are those numbers. The numbers that come from the entropy difference of the extreme point can be solved from some coherence.
But this equality is an assumption.
Sorry.
Suppose they are the same.
Yeah. Right. So I explained this in a way that sounds like we need an assumption because I didn't get the time to introduce a very important trick. That's a merging of quantum Markov state. That actually can be proved under very general conditions. So that one is come from quantum information. And then once we have that, then we don't have any more assumptions direct from the axioms.
So the maximum, the state with maximum entropy, does it also in some sense is a state, just like the angles?
Yeah, you got it. That's an important thing. Originally, when I first worked on this, that was the big puzzle that occurred to me. It's like, why? Well, that seemed to be the case. And if that's the case, everything seemed to make sense. But then I need to look up what's the right thing, and I go to a conference, and someone go to my poster with another collaborator of fusion rules from Entanglement. Kotaro Kato come to my my poster and actually he knows the technique about merging quantum state. I learned from him. And later on, yeah, that's it.
So that will be the result of the merging.
So maybe I should write the merging statement to complete today's lecture, although it's already 2 hours.
Yes, you should complete it since I was like some of what happened.
Another one. Okay. And the statement is that yeah, we can merge the two states. It turns out there is a way to merge states. In this case, we have ABC, ABC, then endless. BCD then endless. And we merge them, we get some state in the two-hole disk. Yeah. It turns out that that's the maximum entropy state. Merging is a claim that we have two Markov states. Your ABC is a Markov state and BCD is another one, such that rho BC, the rho reduced to BC because the lambda reduced to BC. And they are Markov, meaning other words, FAC conclusion of rho is 0, and I BC conditional C of lambda is 0. Yeah, if that's the case, you can merge. We can this unique state of ABC such that the rho reduces to rho and lambda on the subsystems, and the last one is saying tau is another Markov state. With respect to the partition with A and B combined together, and A, B, and D conditional C equal to 0 and equal to another thing. Of tau. Zero. Yeah. So given some state on the subsystem, if they match in the middle, we can merge them to get some state. So this is called merging lemma. And this works for the general tripartite state. So you have a tripartite state, another one. You can merge this, and you get some state tau on a partition of 4 pieces. Stay on tensor product of 4 Hilbert spaces. This is completely general, but it's slightly weaker than what we need. So there is a stronger statement called the merging theorem. Yeah, it says if we take rho and lambda from information common sense. And lambda BCD from information common set of BC and D. And I suppose they can merge. Suppose they can merge according to the merging lemma, then the resulting merged state will belong to the information common set having A, B, C, and D. Yeah. This takes a bit more work, and the proof is written in the paper Fusion Rules from Entanglement. Mm, yeah, so this is essentially what I want to say today. But let me also spend 3 minutes to, yeah, briefly say what's the connection of this to the later part of the talk. So I talked about the fusion today, anions and fusion rules. I guess I forgot to define the anti-anions. Maybe we will cover this in the tutorial or something. But today I try to define anions and fusion rules and try to derive some non-trivial consequence, like the entropy difference is quantized according to some constraint. But we didn't answer about braiding statistics. The anion is about the braiding, the non-trivialness of the braiding property. That's another topic. Braiding. I think this will be on Monday's talk. And the face of matter. Yes, the topological order is about the faces of matter. How is the entanglement bootstrap relevant to the classification of faces of matter? I think I'll talk about this in Tuesday. And the anion is not the full set of data for topological order. There will be kernel response. The kernel response detected by the kernel central charge is also related to the fact that the boundary will be ungappable. That gives me a chance to talk about some development of gapless systems. And this is to be certain. And the merging, just give a quick overview of this one. That merging not only allows us to merge state to get the annulus, get the total disk, merging pieces. But actually, it also allows us to define quantum state on an even more weird state region. This is a region that's not globally embedded in the reference state. So we don't even know whether there is a vacuum or not. But it turns out the study of the state on the inverse region is related to the braiding property of anions. Okay, this is the end of my talk.
Other questions? No questions?
Suppose we have different orders of merging 3 of these annulus together. Do we exactly get some application?
Good question. I think the short answer would be that F move data is more settled than that.
Okay.
So because density matrix is a set that the Brian had, so it's a sometimes it makes some phase information about the phase factors. There's a more clever ways to restore it, but it's more than what you just sketched. Any questions from the Zoom?
So the model evaluators has anything to do with this? I mean, the reference state will be the power.
Model invariance.
Yeah.
Okay, good. So actually you can consider so you can consider the contact of the first contact.
Yeah.
And then you can invert it.
Well,